Good evening, students. I'll start with the class. In the previous class, we had seen what is stress. Stress was nothing but force upon area. So based on this, we saw three types of stress. One was the tensile, or also called as the longitudinal. Then next one was the bulk or volume stress. The third one was shear stress or tangential. This was related to the length. This was related to the volume. This was a shift from the original. Then same we had for tensile stress, we had strain. Strain is nothing but change in dimension upon your original dimension. So for tensile, this would have been, strain would have been delta L upon L. Again, this would have been delta V upon V. And this is again delta L or delta X upon X, or which is also equals to tan theta. This is X or L upon L also. Then we saw what is modulus. Modulus is nothing but stress upon ratio of stress upon strain. Now based on, again, there will be three types of modulus. One will be for tensile, one will be for bulk, and one will be for shear. So for the tensile one, it is called as Young's modulus, and we already derived a formula for Young's modulus. So that was nothing but Y was Young's modulus, stress upon strain. So F upon A upon delta L upon L, either this, or we had substituted the formula for area. So in terms of area and all, and it is force is mass into acceleration. So acceleration due to gravity would be mg, the load, and this is L upon pi r square, either this or this. Now this was for longitudinal stress and this and strain. The second one, volumetric modulus or bulk modulus. Definitely modulus related to volume, stress and strain. I think I've got disconnected. Just This is the formula which we already derived for the previous one, Young's modulus. Now today we'll be doing this. The second one related to volume is called as the volumetric modulus, or also called as the bulk modulus. So the diagram, same one which we used for volume stress and volume strain. So if V is the original volume, so let the body be subjected to external force. So we know that stress will be nothing but force upon area. Now this force upon area is also the formula of pressure, okay? Over here, so this will come under pressure because from all the sides we are applying force. So there is basically a pressure which is applied on the body. This some they express it in terms of pressure also, which is also equals to pressure. So it's like an additional pressure to it. So sometimes we can also write volumetric stress is nothing but some kind of additional pressure on the body. Let one be the new volume. Therefore, change in volume will be delta V. And what is volumetric strain? Is change in volume upon your original volume. This we have already seen, strain formula. We will write what is the formula for bulk modulus. Modulus formula is nothing but stress upon strain. Modulus equals to nothing but stress upon strain. Two ways you can write. One is force upon area, or force upon area we have used as dP, additional pressure. So it will reverse V dP upon delta V. That is equal to your bulk modulus. With the pressure you can use this, or force upon area based on what is given in the problem to calculate. Suppose directly pressure is given, then you can use this formula. If force and area is given, then you can use this. So this is Young's modulus for. If you know the formula of stress and if you know the formula of strain, you can always find modulus, stress upon strain. Just substitute and you'll get done. Same way, the third one is the shear modulus, also called as modulus of rigidity. Nothing but shear stress upon shear strain. If anybody asks you to define, then it is simple. Same. You have to just write the ratio. It is defined as the ratio of shear stress to shear strain within elastic limit. This is the only extra word you have to add to the formula. You can do like this. And then slight shift you can change. This face remains fixed, and then this fellow shifts. If you're not comfortable drawing the 3D one, simply draw the normal one. How I done before. Like this. In the previous class, I had given you 2D, no? You can draw that also, no problem. This will be theta. This angle will be theta. It's just that this is a fixed face, and this whole box top part will shift. This is the delta L. Okay. So you know that shear stress is nothing but force upon area, F upon A. Then we will write what is shear strain. Shear strain is tan theta, which is equals to if theta is very small, you take tan theta almost equals to theta 1. So it means that theta equals to delta L upon. So we know stress, we know strain. So just substitute here both the places. Stress is force upon area. This is how we have y, no? You can write on top of the n cube, you can use this letter. Instead of that, we can use theta also. Okay, so we have derived all the formulae for Young modulus, then bulk modulus, and modulus of rigidity or shear modulus. Next, we'll see what is the elastic behavior of a body. Okay, don't write, but first I'll just explain. So we have seen what is called as Hooke's law. Okay, what does Hooke's law say? Stress is directly proportional to strain. Okay, so what will happen as the stress increases, the strain will also increase. Okay, if you are decreasing the stress, then the strain will decrease. That is within the elastic limit. Now, if you try to plot a stress versus strain graph, proportional means suppose if I'm not I'm just marking the numbers, but while explaining, you don't have to draw the numbers, just to explain to you. So what happens is if I'm suppose increasing the stress or strain by 1 unit, the stress will also increase. If this is 2, then this will also be 2. So something like that. So what is going to happen? There will be a linear change. Okay. So like this, it will keep on increasing because they are directly proportional. As you increase the stress, the strain will also increase. Now this happens whenever the body is within its elastic limit. The moment you remove the stress, whatever got extended should go back to its original position. Consider the rubber band. You are stretching the rubber band. The more force you apply, means basically the more stress you are applying, there is more change in the dimension. The length is increasing. Now you leave the rubber band again. Slowly, if you are decreasing the strain, slowly if you are releasing the force, it will try to come back to its position. So from here it will come back to 0. So from here suppose to some point You can take it as P here. Okay, then what will happen is after a certain elastic limit, what is going to happen? If you still stretch the rubber band, slowly it will start losing its elastic strength. Okay, so even if you remove the strength, the stress, still it will get stretched. And then at certain point, what is going to happen is it is going to fall off. Means it is going to break. Now suppose you consider a wire. The wire is hanging. You have attached some load to the wire. The wire will try to stretch itself. Now the moment you remove the load, if it's within its elastic limit, it will go back. But if you keep on increasing the load, suppose to a beyond a limit, what is going to happen? Slowly this wire will get stretched, and then even if you remove the load, then it will release all its elastic property, and then still this wire will keep on getting stretched under its own weight, and then at some point that wire will break off and it will fall off. So from elastic, then it goes to plastic. Till this part it is like elastic, it goes back. But at this point it doesn't, once beyond it crosses this point, that rubber band will not come back to its original position. It will lose its shape, and still if you keep dragging it, it will break. Okay, so there's not exactly like this. I'll show you the correct graph. So you can just draw the graph first, and then I'll give you the explanation part. Share the graph. Only don't write the points. Otherwise I'll draw and give it directly. This you all draw now. This is called elastic limit. Obeys Hooke's law. It's almost straight, huh? Like slight bend, but almost straight. This is stress. This is strain. After the elastic limit, whatever is there, from here on it is plasticity. This is elasticity. And point A is called as proportionality limit. So till here, what is going to happen? It obeys Hooke's law. From here onwards, the Hooke's law is not valid. From here to here, the moment you remove the stress, this stress, it will come back to its position. I'll give you the explanation of the graph point wise. When load is applied on the wire, for each load, the stress and strain is determined. Determine is calculated and graph is plotted. Now, portion O, from O to A, that straight line is showing that stress.
Excuse me, miss.
Yes,
Miss, that is the stress and strain it is.
yes, and strain is determined as the graph is plotted. Now from O to A, you can see it's a straight line showing that stress is directly proportional to strain. Point A is also called limit of proportionality, as Hooke's law is obeyed till point A. Now portion for portion A to B, graph is not a straight line. That is, Hooke's law is not obeyed between point A and B. Till point A, there is a limit. So at the moment this point A it reaches, its limit is reached. Now no more proportional. Then it will be slightly different from a straight line. So Hooke's law is not obeyed then. Still, even after point now B, if you keep on increasing the force of the load, so if so now what happens till point B, what you can do, you can remove the load, it will come back to its original position. If wire is unloaded, unloaded means the load is removed, still it is there within its elastic limit. Till point B, it is there within its elastic limit, even though if it's not obeying Hooke's law, but still there is elasticity. If the wire is unloaded at point B, the graph between stress and strain follows reverse direction. What happens? It was increasing, no? The same thing you will come back to its original position in the reverse direction. First, if you were increasing, it was going like this. Now you start removing from point B. The moment you remove the load, it will come back. It's like the rubber band will come back to its original position. Along B, A, and then O. From B it will come to A, and from A it will come to O. Point B is called elastic limit. Yeah. Now what if you remove the load at point B, it comes back. Now what if you keep on increasing even after you reach at B, still if you keep loading the wire, if wire is still loaded beyond point B, the strain increases faster than stress? What happens now? The wire has become very weak in nature. So even if you put very small stress, no, strain will be more. Strain means what? Increase in the length of the wire. Even if small force you are applying based on the load, there will be lot of pulling of the wire, because now the wire after B becomes very weak in nature. So if the wire is still loaded beyond point B, the strain will increase faster than your stress. First it was what? Proportional. How much ever force you were putting, that much only length was increasing. But now for small one, this increase in length is still large. Now if we remove the load at point C, now what is going to happen? It will not come back to its original position. It may not follow the same path. Okay, the graph of stress versus strain. So in a graph now, just put this. This was a graph now. This was B, then this was C. So just put like this. It may not come back to its original position, but slightly deformed. You can put this as O dash. And in a graph now, from point C, just draw like this and put it as O dash. So it will not come back to its original shape. It will come back, but to some different shape it will. Not exactly to the original shape how it was. So if we remove the load at point C, the graph of stress versus strain will not follow the original path. But instead will be along CO dash. It will not follow that CBAO path. Instead, it will follow CO dash. It means even if stress is zero, stress is zero means load is removed. Strain is not zero because there is some change in the length. From point B, if you remove the stress, strain also will come back to zero. But here, if you remove the stress, means remove the load, still it is not coming to zero. Some strain will be still there. This from O to O dash. Strain is not zero. This it means even if you can use the word. Even if stress is zero, the strain is not zero. It indicates that the material has got deformed. That the body is deformed now. It's not like what was there originally. And this deformation is said to be plastic deformation. Now, on further increasing the load, suppose if you still increase the load beyond C, the strain begins to increase even without increasing the stress. What happens is after this particular point, even if you keep the load there, you are not increasing the load also. Okay, without any stress also, still the wire will keep increasing. Because the body is plastic in nature now. Even if small force, there will be a lot of change. In the last one, now beyond level D, the wire loses its shape and becomes thin in diameter and ultimately breaks at point E. Okay. So this is the explanation for the graph. There's a word called what is elastic fatigue. It is defined as like elastic fatigue will be like how there's a bridge. Okay, after many years, what they say is like you have to always change or do some repairing of the bridge. Why? Every day there is a movement of the vehicles, so it is subjected to continuous stress. So the stress will cause some strain, small strain, minute strain, but over a long period of time, what will happen? It will have fatigue. Fatigue means even a person will faint. Okay, why? Because there is some limit. Suppose if we have no energy left, then it is normally called as fatigue. The same way, even any body would have its elastic fatigue. Consistently, if it is repeatedly given some stress, at some point it will lose its elasticity and then break. Same like that bridge. Everyday vehicles will go over a long period of time. There are chances that the bridge will collapse. It is defined as the loss of strength of material caused due to repeated alternating strain to which the material is subject. Consider a wire only, a bending wire, normal. So if you keep bending, you just bend a wire, then you again stretch it, bend a wire again, make it straight, bend a wire again, make it straight. If you keep doing that, at some point it will lose its strength and then it will break. And solve problems. So theory part is done. Only problems are left based on the chapter. First question. These are based on Young's modulus, okay? Related to longitudinal strain. First one, Young's modulus of the material of wire is 1.2 into 10 raised to 11 Newton per meter. Find extension in the wire of length 3 meter and cross sectional area 4 millimeter square when it is suspended vertically and load of 8 kg is attached to its free end. So the moment you see Young's modulus, you know that it is related to the longitudinal strain. So you have to know that formula. So y is 1.2 into 10 raised to 11 given. Length is 3 meters. Now cross-sectional area, cross-sectional directly area has been given now. Now here you have to be very careful. This is millimeters. Your normal standard unit should be in terms of meters. You have to convert this. You know that 1 millimeter is nothing but 10 raised to minus 2 meters. Now here again it is 10 raised to minus, this is square. We'll have to square it. If it was just millimeter length, then it would be 10 raised to minus, but this is area, so square means you have to square it. This will be 4 into 10 raised to minus 4, it will be meter square. Load means straight away, you know, it is anytime we put a load, you know, it's mg. The mg value is 8 kg. Now use the formula. The formula is y is mgl upon pi r square delta L, or I told you this you can use straight away as area. Pi r square is nothing but your cross sectional area. So find extension in the via means what has been asked, delta L. So substitute all the values. Mg total is 8 kg. Then length already given, that is 3 meters. A mass of this has been given now, wait on. If you have to see, check here. Load has been given 8 kg. But suppose if it is given in terms of Newton, no, then only we have to take whole thing, the weight. Now it is given in terms of kg. So kg will be only mass. If this was given a load of 8 Newton, then mg would have been 8 Newton. If kg is given, then it is only mass. So we'll have to use, so now only m will be equals to 8 kg. So load, so then we'll have to use 9.8. I have not seen the unit here. If this is Newton, then only it would have. So this will be 9.8. This is length. Length is 3. Area will be here. 4 into 10 raised to minus 4. Delta L we have to calculate. So delta L you take up. Now we'll calculate it.
Teacher, 1 millimeter is equal to 10 raised to minus 3 meters, right?
Minus millimeters. 1 second. This is centimeters, no? Yes. So that will be 6 then. It's correct data. A centimeter will be 10 raised to minus 2. Correct. Huh? So this will be minus 6 then. That will be 4 into 10 raised to minus 6. If it was centimeter, then it would be 10 raised to minus 2. So we'll multiply this. This is 8 into 3 will be 24. 24 into 9.8. Or directly we'll cancel this. 4 to 0.4, 0.2, 0.1, 0.1 is divided by 2. So 2 4s are 8, 4.9. So 1 decimal I'm shifting here, 1 decimal I'm shifting here. So 49 upon this will be anyways 1. And this will be powers will be added 10 raised to minus 6, 10 raised to 11. Take it up. This is 5, 10 raised to minus 5 Newton. 49 into 10 raised to minus 5 Newton. Both were decimal, so I just shifted one here, one here. They became normal number. Second one, a wire of length 2.5 meter and a diameter of 0.8 mm is stretched by a load of 10 Newton. Find extension of the wire. Y is given as 2 into 10 raised to 11. Different materials will have different Young's modulus. Now diameter is given mm. So radius will be 0.8, and this will be 10 raised to minus 3 upon 2. Now there is no squaring because this is simple mm. If it was area, then it would be square. That will be meters. Now it is Newton. Now you see, Newton means along with the gravity. We are multiplying already with the force. So mg value will be now 10. If it was kg, then we have to multiply it by 9.8. Now just keep it as 10. Y is already given. And what is the delta L extension asked? Now we cannot use that area directly formula. We'll have to use 2 pi r square. Pi r square is there, no? So this will be mgl upon pi r square delta. Now we'll have to substitute r. Pi can take 3.14 or 22/7. This whole thing will be 10. Length is 2.5. There is square now into 10 raised to minus 3 the whole square into delta L. This will go up, 7 will go up. Delta L is here. So 7 into 10 into 2.5, 22 into 0.4 the whole square. And this square means double, it will become 10 raised to minus 6. This will have brought down to 2 into 10 raised to 9. So numerator will be 70 into 2.5. Forty-four into 0.16. 175 divided by 7.04. So 24.8 into 10 raised to minus 5. You can some places you can write like this also, 2.48 into 10 raised to minus 4. This is also correct. Third one, a steel wire of diameter 1 mm and length 2 meter is stretched by applying force of 2 kg weight. Calculate increase in length. Second is strain. Third is stress. So diameter 1 mm, the radius will be 0.5, half of this into 10 raised to minus 3. Length is 2 meters. Now what is been said? Applying a force of 2 kg weight. Basically, whenever you have something like this, you come across, what we have to do is we have to convert it into newtons. So this is in terms of kg. Force is normally given in terms of newtons. So weight means obviously in terms of kg, I told you mg should be equals to in terms of newtons. So what is missing? If you want to convert it in terms of newtons, you have to multiply it by 9.8. So that will be in terms of newtons. If it was 1 kg, then it would be 1 into 9.8. If it was 10 kg, then it would be 10 into 9.8. So basically, mg is nothing but this much. You take the formula and substitute. Young's modulus given in the bracket y is 2 into 10 raised to 11. First one, increase in the length, then the strain, and then the stress. So straight away I'll use this. So y I brought here, delta L I took this. Length is again 2 meters. We can use 3.14 also, no problem. This will be 0.5 to 4 into 9.8. I can cancel also with this one. Before that, you can write it as 4 also. Or you can keep no issues. So 2 into 2 into 9.8. This will become 0.25. 0.5 square will be, basically you have to square 5, that is 25, into 10 raised to minus 6 into 0.25 into 2 will give me 0.5 into 3.14, 1.57, 39.2 divided by 1.57. 24.9 into 10 raised to minus 5. You can write like this also, 0.249 into 10 raised to minus 3. If you come across like this, I'm saying. There are various ways. Even if you write like this, no one will cut mark. This is also correct. This is also, instead of 10 raised to minus 3, sometimes they may use mm. If you come across like this, this is also correct. You can keep your answer like this also. Now your first part is done. Next is your strain. Strain formula is nothing but simple change in the dimension upon your original dimension. So 24 divided by 2. Half of 24.9. So that will be 1, 2, 4. And the last one, stress. Force upon area. Force is, you know that, it's mg. Mg was how much? 2 into 9.8, 3.14, 0.5. Calculate. Strain has no unit. Huh? Stress, you can write the Newton per meter square. Next one. What mass must be suspended from the free end of steel wire of length 2 meters in diameter 1 mm, stretched by 1 mm. Y is given as 10 to 10 raised to 11. Now mass you have to calculate. half of 1 will be 0.5. Stretched it by 1 mm means delta L is 1 mm. And we have to calculate. So everything will go this side. And this will come down. So 3.14 into 0.25. 0.0 10 raised to there is 6 now. This is also there. I forgot this. -6 -3. This is there. 1, 2, and 3. It will be 2 now. Mass that will be kg. Basically, when we multiply this, it will be 8 kg. Because 2 decimal places will get shifted. Last one. There are 2 wires of same material. Their radii and length are both in the ratio 1:2. If extension produced are equal, what is the ratio of the load? Two wires of the same material. Same material means same Young's modulus. So you can take material 1 and 2, no? So y1, 2 wires, no? So y1 will be equals to y2. Radii r1 upon r2 is in the form of 1 is to 2, 1 upon 2. Same way length L1 upon L2 is also 1 by 2. If the extension produced are equal, extension means delta L1 for wire 1 and delta L2 for wire 2, then delta L1 will be equals to delta L2. Extensions are equal. So what will be y1 as per the formula? The y we know that it is mgl upon so everywhere we'll have to put 1. So mg1 will take the load. m1g. G is anyway same. Same way y2 will be, can take it as mg1. This will be mg2 load, whole load. L2 upon pi r2 square, everywhere will leave 2 for the second wire. This is formula for first wire, this is formula for second. What you can do is just divide y1 upon y2. Equation 1 you divide by equation 2. Or 2 upon 1 also you can do, no problem. Now these are equal. So what I can do is just take both as delta L only. So delta L1 is equals to delta L2. And take it as delta L. So this and this will cancel. Pi and pi will cancel. You can, if you want, you can calculate G and G also. Because gravity 9.8 will remain the same. So what remains is this will reverse. Now we'll write all the terms one below the other in the correct order. I'll write m1 upon m2 first. All are multiplication. Then L1 upon L2 I'll write. And R2 square upon R1 square. Again, this also is equals to y. You can take it as y only. It will cancel. Y1 equals to y2 equals to y. So here it will get the answer as 1. Because Young's modulus for same material will be equal. So that will be 1. Now this is what we have to calculate, ratio of their load or mg, whatever it means. And now this is L1 upon L2 is already given to us as 1 by 2. R1 upon R2 is 1 by 2. So what will be R2 upon R1? 2 by 1. Because this is ulta, R2 upon R1. And there's a square. Two square will be 4. Now take this side. Ratio of the load. 1 by 2. That's the answer. I'll stop here. I'll continue with the problem on that bulk and shear modulus in the next class, and I'll finish with the chapter.